We're working on another real ideal battery problem here. Also, this one has a switch. So we want the terminal voltage of the battery, which would be the voltage if we had a voltmeter like this, in each switch position. And we have an ammeter in the circuit with readings for each of those, so that's nice. So in the open position, when the switch is open, current flows through the battery, down through here, back through the battery. No current flows in this branch because it's not a closed loop. So the delta V across the resistor, we can just get by Ohm's law, 1.636 amps times 5 ohms. That voltage is 8.18. It's negative because it's a drop. Negative 8.18 volts across the resistor. Well, if I look at the loop rule, all there is the battery and the resistor. So 8.18 volts is the terminal voltage of the battery in the first case. In the second case, when this switch is closed, there is current flowing. But there's also still a loop that I can make like this. So whatever the voltage is across the 5 ohm resistor will be the voltage across the 10 ohm resistor as well, because they're in parallel, and the voltage across the battery by the loop rule. So same deal, I just need to use the updated current, 1.56 amps now, times 5 ohms, which is negative 7.83 volts, so we got a little sag in the terminal voltage as the total current increased. The current through this branch decreased, but the total current is bigger because we have two paths now to follow. So as we expect, when there's more current through the battery, the voltage, terminal voltage will sag. Okay, we want the EMF, that's this voltage here, the open circuit voltage. By open circuit, we don't mean the switch being open, I mean when there's nothing in the circuit. So you put meter leads over it, there's no current flowing through here, so that's the voltage that we get. And the internal resistance of the battery. You can do this algebraically by setting up a system of equations, because if I do the loop rule, I start here and go through, I get the EMF minus I times R, that's the I total, times R, minus, if I go through this first resistor, we figure out that was 8.18 volts, or sorry, I wrote ohms up there. Volts. 8.18 volts. And that got me all the way around, so that's 0. So that's I1. And that current is known. Right? It's only one loop, so that's the total current. Minus 1.636 amps times R minus 8.18 volts equals 0. So that's an equation. There are two unknowns, EMF and R. So I can set the thing up also for this second loop, but if I'm going to do that, I have two branches that I need to worry about. So when I set this up, I2R minus, and then I can go across this one branch here, 7.83 volts. I'm going to have to do some calculation first to figure out what I2 is, because I only know I through this one branch. So I need to figure out what I is through the other branch, and then, right? So once I do that, I can do two equations and two unknowns. That's a fair amount of solving, and you know, if you're up for that, go for it. Be my guest. Second method, I can use an IV curve, right? So there's the EMF is the ideal voltage, right? And then this thing slopes back. The slope is negative 1 over R, right? Well, I have 2 points, right? I can figure out the slope of this graph. The slope of the IV graph is, so it's rise over run, so this is 2 minus I1, V2 minus V1, that would be terminal voltage, right? So the terminal voltages are the two that we got, 8 volts minus 7.83 volts, and the currents, though, are the total currents. So we have one of those. That's for the, let's see, 7.83 volts minus 8.18 volts. We have one of those. We have the one that corresponds to 8.18 volts. So that's 1.636 amps. We do need to figure out what the current is through the other one. So either way, it looks like we'll need to do that. Okay, so there, well, I know that the voltage change across the resistor is 7.83 volts. The voltage change across that resistor is 7.83 volts. Over 10 ohms is 0.783 amps. So I is 0.783 amps plus 1.565 amps, which is what we had in the other branch. 2.348 amps. Okay, so if we do our subtraction on the top, and then our subtraction on the bottom, we're going to get a slope of negative 2.03 amps per volt, or negative 2.031 over ohms. Remember that R is negative 1 over the slope, which will be 0.492 ohms. Once we know that, we're in pretty good shape then to find the EMF. So I'll just take maybe the first case, so that I know the terminal voltage, 8.18 volts, is the EMF minus IR. I through the battery in this case is 1.636 amps, times R, which is the internal resistance, 0.492 ohms. That is 1.14 volts. So this EMF is 9.32 volts. And that would be, if you had a fancy way to find your intercept, that's what it would be, if you're thinking sort of real geometrically about it.